So yesterday we ended up talking about Lewis structures and joint organic molecules a little bit, and we are going to continue that today. And also we talked a little bit about the electron configuration. So I hope everybody remembers now this little trick here, and that the arrows gives you the directions in which you fill up the orbitals, so with electrons, and the s orbitals can carry 2 electrons, p orbitals 6, d orbitals 10, and f orbitals 14 electrons. Okay, yes, Chantel?
So how do you know, or like what is it that makes each shell holds a certain amount? Like, is it like space-wise or?
It's based on the number of the possible combination of orbitals. So there's only one s orbital, which is the spherical orbital, and of course, depends on the shell. It's gonna be, larger in diameter, and it's gonna have some nodes, but in general, it's a spherical shape. Okay, for the s orbitals. For the p orbitals, and we're gonna talk about this today. They look like little 8s. Okay, and the d orbitals, they are combination of 2. What looks very similar to p orbitals, but they are not p orbitals. Yeah, so it all depends on the actual shape of it. We will focus only on s and p orbitals, and I'm going to talk about it later. Yeah, but the idea is that each and every orbital can carry 2 electrons. Since there's only one type of s orbitals, that means only 2 electrons can be stored on the s orbitals. Then on the p orbitals, you have px, py, and pz orbitals. So therefore, there are 3 different p orbitals, depends on the orientation in space. And because of that, each and every one can carry 2 electrons. So 3 times 2, that's 6 electrons. There are 5 different d orbitals. So there is the for example, dz square orbital. Yeah, so that's one of them. And there's the dx square minus y square. And there is there are some other ones too. That it doesn't matter at this point. You don't have to be worried about the d and f orbitals and their shapes. What you need to be familiar with is an s and p orbitals. Okay, and the only thing you need to remember, and this was mentioned in general chemistry too, that what is the maximum number of electrons per each and every type of orbitals. Okay, so 2, 6, 10, and 14. Okay, so I hope you remember that using this little guideline here, that once you follow the arrows here, this is the way how you fill up the different orbitals with electrons. And again, as long as you remember that s, p, d, and f orbitals, they carry a maximum number of certain, like a set number of electrons, you can fill up all the subshells, and then give me the electron configurations of the element. You also have to keep in mind that if you have, for example, an ionic species, like for example here we have a calcium 2+, that means that 2 electrons have been removed from the neutral atom. Okay. Therefore, the electron configuration of this calcium 2+ will have 2 less electrons, and will have the noble gas electron configuration, which in this case is, I believe, argon. Yeah. And if it's an anionic species, so let's say an S2-, for example, that means that you have to add 2 electrons to the electron configurations to obtain again the noble gas configuration, which is gives you the octet on the valence shell. Okay. We also talked about a little bit about the electronegativity. And how does it affect the type of the bondings that is formed between 2 elements? So we know that if you have a big difference, so it's over 1.7 difference in electronegativity between 2 elements, then the bond that forms between these 2 elements is an ionic bond. If it's less than 1.7, then you have a covalent bond, and if it's between 0.5 to 1.7, that's polar covalent bond. If it's below 0.5, and then it's a non-polar covalent bond. Okay, and based on that, you can just basically, like in this problem here, you look at the different elements of fluorine and sodium, for example. Here, you see the sodium 0.93, fluorine 3.98. So there is like the difference between them is 3 units in electronegativity. So definitely this is a polar, this is the ionic bond. Okay. And so on, so on. And the combination here between, let's say, sulfur and chlorine here, you see this is going to be what about 0.5. So so that will be non-polar covalent. And so on, so on. And then we talk about Lewis structure, drawing proper Lewis structures. So the first thing you want to do is that you want to check out what is the main group number for your element. Because that will give you the number of valence electrons in your molecule. Then you draw this, those elements with those electrons around, and then you try to connect them together with whatever remaining elements do you have there, yeah, to make sure that all of the elements have the octet, and the hydrogen has 2 electrons on the valence shell. And if you can do that, then you will have a proper Lewis structure. Of course, you can draw the Lewis structure not only for neutral molecules but also for ions and so cations, anions, and more complex, let's say molecules. And we're going to have some examples of those just in a moment. And also we talked about the general formula or molecular formula. So the molecular formula gives you the information about the number of the elements that are involved in the structure that your structure consists of. But it doesn't tell you anything about the arrangements of those. So like in the example A here, for example, the same general formula allows you to draw 3 different molecules. And that's important. Okay, so there is an error here in this formula, and it should be 5 here, not 6. And I'm going to so please, when you do some of those problems by yourself, just please make sure you correct it. Okay. Talked about the degrees of unsaturation. So when you have a general formula and you want to predict how many numbers of the double bonds do you have there, or the pi bonds, let's call it this way, and you need to calculate the degrees of unsaturations, and it's calculated using the formula over here, which is 2 times carbons plus 2 plus nitrogens minus hydrogens minus halogens divided by 2. And like we did it in this molecule C here, and we found out that we have 5 degrees of unsaturations. And so the double bond here, that's 1 degree of unsaturations. 3 double bonds in the ring, that's another 3 degrees of unsaturations. And the ring itself is 1 degree of unsaturation. So you need to remember the ring itself can be a degree of unsaturation. And this is something you want to practice because, many times people make mistakes here. Very often, if you have a molecule that doesn't have too many hydrogens and it has 4 degrees of unsaturation, it means that it's gonna be a benzene ring. Okay. So let's move on now to the next problems here. So we're gonna do problem D now. So we have C2H5OH. Okay. So normally, if you were to write down the molecular formula for that, it would be C2H6O. Okay. So by writing OH means that this OH is actually this OH is in a hydroxyl group somewhere in your molecule. So you draw the Lewis structure of this molecule will look like this. Then you have a carbon, and you have an oxygen. This oxygen, we know that it's connected to hydrogen already from the general formula here. Each and every carbon has 4 valence electrons. Oxygen has 6, but 1 is being used to form the oxygen-hydrogen bond. So you just draw 5 here. Okay. Then we have 5 extra hydrogens. So if you look at this molecule here, first you want to connect it with your central atoms here, which is the carbons and the oxygens here, and you just count number of unpaired electrons, and you have 1, 2. It's 1, 2, 3, 4, 5. So that basically makes it very simple for you, because all you have to do is just draw 5 hydrogens around those carbons and then just connect them together. So this is the structure of ethanol. The line angle formula for that molecule will look like this. Okay, so carbon. Let's say that this is carbon 1, this is carbon 2. So carbon 1, carbon 2, and the oxygen. Okay. The condensed formula for the ethanol will be CH3, CH2OH. That means that this is the carbon 1 now, this is carbon 2, and so carbon 1 is connected to 3 hydrogens and carbon 2. Carbon 2 is connected to carbon 1 and 2 hydrogens and the oxygen. And oxygen is connected to hydrogen and carbon 2. This is how you read that. Okay, and the next question would be D, I think, yeah? So in the D molecule here, we have a condensed formula, okay? So from this molecule here, you can see that we have the CH3, CH2, CO, CH2, NH, CH3, okay? So that tells you that, that we have a carbon here that is connected to another carbon. This is H, H, H. So this is CH2, CH3 here that is connected to CH2. Then CH2 has to have 2 hydrogens. Okay. So now we took care of this guy here. We took care of this guy here. Now this CH2 is connected to another carbon here that is connected to oxygen, and then another CH2. So knowing that the oxygen has 6 valence electrons, carbon has 4. 3 of them are already involved in the formation of the sigma bonds. So you have to make a double bond between oxygen and carbon here to make this a valid Lewis structure. Then you have an NH. Okay, so you have N and H. Okay, let me correct it here for the hydrogens. I'm just going to draw them, okay? And we have NH, and this nitrogen is connected to CH2 and then CH3 on the other side. So C, H, H, H. Are we done here, or there's something missing in this Lewis structure?
Doesn't N have 5 valence electrons?
So nitrogen has a lone pair of electrons. That's correct in its like a neutral state. Okay. So so how do you know that? Well, again, you count the number of valence electrons. So 3 of them are involved in the bond formations. So that leaves 2 because the nitrogen is in the 5th main group. Yeah. And now, if you want to draw the line angle formula for this molecule, that would look like this. 1, 2, 3, 4, 5, 6 different. Sorry, 1, 2, 3, 4, 4 different carbons here. Okay. We know that at the carbon number, let's call it this one, 1, 2, 3. So at carbon number 3, we have a double bond. Let me move it up a little bit. Okay. Try different color. So 1, 2, 3, 4. So this is 4. At number 2, we have a double bond. And then we have at the fifth position, we have a nitrogen, NH, and the methyl group. So this is the line angle formula for this molecule. Okay, in line angle formula, you don't have to show the lone pair of electrons unless you need it to describe the reactivity of the molecules. Okay. What is the general formula for this, or molecular formula for this molecule here? Anybody? C, you have a carbon, hydrogen, oxygen, and nitrogen. Okay, so how many carbons do we have? 1, 2, 3, 4, 5 carbons. Yeah, so C5. How many hydrogens? Let's start from the left side. So 3 plus 2, that's 5, plus 2, that's 7, plus 1, that's 8, plus 3, that's 11. Yes? Very good. How many oxygens and nitrogens? Just 1. Yeah? So C5 and H11ON or NO. Okay? So let me redraw it here. Okay? So C5H11NO. Okay? So if the question was not written like it is D, but it was given to you as a molecular formula, can you think of another molecule that is different than our initial molecule that we drew here? Okay, so this is our first molecule that we were able to draw with this general formula. Can you draw another molecule that will have the same molecular formula? What do you think? Yes or no? Anybody? Yes or no? The question is, can you draw another structure that has the same general formula or molecular formula, but it's a different structure that we already drew? And the answer is yes. And how many of those are possible? Well, quite a lot actually. But if you think about it, the best way is just just to move move first the carbonyl group. Yeah. So you can draw the same molecule here, and instead of having a carbonyl, in this case the third position, you can have it here. Okay. You can also draw the same molecule that has a carbonyl in here. Okay, and so on, so on. You can move the nitrogen to be a terminal nitrogen, and it's gonna be NH2 then. And of course, it's not gonna be the same as the condensed formula that I showed you here. But again, this would be the answer to the question if I were to give you the molecular formula. Okay. And I think the remaining problem that we have is E here. It doesn't matter if you draw it up or down. So how can you predict that the isomers are possible? And you are talking about the constitutional isomers, yes? Yes. So for the constitutional isomers, it's just basically you need to just look at the structure and see, whatever the first structure you were able to draw, and see if you can rearrange it in the way that it will have the same molecular formula but a different shape, basically different arrangements of the atoms in space. As far as the Jeremiah, yeah. What you are talking about are conformational isomers, and we are going to talk about it in the future. Okay, so these will be the isomers that rotate around sigma bonds, and therefore therefore they have a different shape, depends on the rotation around each and every sigma bond. And as you can imagine, the larger the molecule, the more rotations possible, and the more different conformers are possible for each and every molecule. Okay, so in here now we have another molecule that consists of carbon, sulfur, and oxygen, yeah, and hydrogen. So how do you know how to draw the Lewis structure of that? Well, you start with the back part here, which says SO4. So that gives you an idea that this must be some sort of sulfuric acid derivative. Okay, so again you have a sulfuric acid with 6 electrons, and then 4 oxygens around, each and every one with 6 electrons again. Same group here. Okay. Okay. So that will be your first step here. Okay. What you need to do now is just you need to connect the molecules. The atoms first with the sigma bond, and then, if possible, with a double bond here. Okay, it doesn't matter if you connect the oxygens that are top and the bottom, or the sideways in this case. Okay, and then you have 2 methyl groups that are left. So it's CH3 each. So that means CH3, 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 and then you have 1 electron left here, and another CH3. Okay. And those 2 electrons now can be paired. And as you can see here in this molecule, all carbons, oxygens, and oxygens, they are happy here because they have an octet. Sulfur has the extended octet here. And then we have the hydrogens that have 2 electrons each. So this is the dimethyl sulfate here. Okay. So if you compare this to, for example, to this molecule, CH3SO, okay? Well, now you have a slightly different situation, okay? Because now you have a sulfur that is a central atom. You have the oxygen with 6 electrons. And you also have a carbon. I hope everybody knows by now that CH3 with 1 electron. And the I'm sorry, 2 CH2s, yes, correct. Dimethyl sulfate, sulfoxide in this case, okay? So thank you. Why? Oh, because this is the molecule. This is the actual molecule. This is something what's called a polar protic, so a polar aprotic solvent. Very commonly used in organic synthesis. Okay. So now you have this guy here. Okay. Yeah, the formula is CH3 2 times. So that means it's 2 times CH3. Okay. So this 2 tells you that there are 2 of the methyl groups. Okay, and then the sulfur here has 6 electrons. Yeah, so 4 of them are involved in the formations of the bond, and this is your Lewis structure of dimethyl sulfoxide. Okay, even though this is the single bond, this is the double bond. Actually, in reality, this is more like a very polar single bond. Okay, so there's an O minus and S plus here, but don't worry about it. Okay, that will be the structure that I will be looking for. Okay, so I think we did that already. So I'm going to erase that and then just give you another. Yes, Grenade?
Yeah, Professor. In the question it says, I think they're asking for a line angle formula.
Yeah, well, for the line angle formula here, that will be this one. Okay, and for the other one, it will be this guy here. Okay, so the only thing you need to do is just need to get rid of the methyl groups here, because the rest has to be this, has to be shown on line angle formula. So when you draw line angle formulas, you only abbreviate the carbons and hydrogens. Heteroatoms remain the same, and of course you need to show double bonds, triple bonds, and whatever other bonds that are present there. Okay, sorry for that. Yeah, so. So how about this molecule then? Let's say we have the CH3 C C CH2 CN. Okay, so this is the condensed formula of the molecule that I want you to draw. Okay, so. So what happens here? Okay, so the first thing you do is just like, of course, you see that if we label the carbons here, 1, 2, 3, 4, 5, the carbon 1 is connected to hydrogens and carbon 2. Carbon 2 is connected to carbon 1 and carbon 3. Carbon 3 is connected to number 2 and carbon 4. Carbon 4 is to 3 and 5. Okay, so this is the first thing you need to draw. And in order to do that, well, you just draw yourself 5 carbons, okay, in the chain, okay, because we know that this is 1, 2, 3, 4, and 5. We know that carbon number 1 has also 3 hydrogens here, so that's easy to draw. We also know that carbon number 4 has 2 hydrogens. Okay, and the carbon number 5 is connected to the nitrogen. Now it all comes to the fact of what happens with the remaining electrons in your molecule. And so carbon number 2 has 2 additional electrons. Carbon number 3, 2 electrons, the valence electrons. Carbon number 5, again, 2 additional electrons. Nitrogen has 4 extra electrons, because 1 is being used to form the bond here. Yeah. So all you have to do is just combine them together. Yes, that's true. It has 4, but in this case, we already drew the bonds between Chantal, between the carbons. So those take 2 electrons from carbon 2, 3, 4, and 5. So if you were to draw the line angle formula for this molecule here, probably the easiest way to do that will be just to draw the line here. So this is your carbon now, carbon 1, 2, 3, and 4. Then you have a carbon number 5. You're going to draw it as an angle, and then you have a triple bond and lone pair of electrons. Okay. We're going to talk about the bond angles in when we talk about hybridization and stuff. Okay? So so don't worry about it too much at the moment. But normally when you have an sp3 okay. We draw it because this is something what's called an sp3 hybridized carbon, and we're going to talk about it. I'm sorry, in the moment. The next thing why you do that is simply because if you let's say if I drew it this way, how do you know how many carbons are there? You know that there's a carbon here, there's a carbon here, there's a carbon here, and there's a carbon here, but there is no way you can find out that there's a carbon also in between here, because for one person it could be that there are like five carbons, over there. For other person, it could be just one. Yes, so that's why you make an angle. So the angle actually indicates that there is a carbon number 4 in this position. Okay. You don't want to do that actually with the triple bonds because the angle between the this is called sp hybridized carbon is 180 degrees. So it's better to just learn to draw the triple bonds as a straight line. And we're gonna talk more about it later. Okay. So at this moment, you just want to make sure that you know that what is the reason why we actually drew those triple bonds here, okay? And the reason comes from the fact that you have to somehow pair all the remaining electrons from the carbons, 2 and 3, and then the carbon 5 and the nitrogen. So so let me go back to this question again, okay? And then Chantel, if you go step by step, okay? So we have a carbon, 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 and nitrogen, okay? Carbon, okay, maybe I will try again. Carbon, 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 nitrogen. This is what our condensed formula tells us. Each carbon has 4 valence electrons. Nitrogen has 5, correct? Now, at the first, and then we have the hydrogens and the, so our condensed formula tells us that there is a CH3, C, H2, Cn. Okay, so our condensed formula tells us that the first carbon is connected to 3 hydrogens. So we have hydrogen, hydrogen, and the hydrogen. That will take 3 valence electrons. The 4 valence electrons will be taken by the carbon-carbon bond. Then we have carbon number 4 here that has 2 hydrogens, and that will take 2 electrons. Okay, and then we also know that the carbon number 2, 3, and 4 and 5 are connected in the linear fashion. So that means the carbon number 3 and 4 and 2 are connected. 3 and 4, 4 and 5 are connected, and then carbon and 9 are also connected. That leaves 2 electrons on the carbon 2 and 2 electrons on the carbon 3. So in order for this structure to be a proper Lewis structure, you have to connect them together. So both of the carbon 2 and 3 can have an octet. So right now the carbon 2 has 1, 2, 3, 4 bonds. 4 times 2, that's 8 electrons, octet. Carbon 3, the same scenario. Now if you look at the carbon number 5 here, again, you have to pair the remaining electrons with the nitrogen. So this way the carbon has an octet and the nitrogen has an octet. Nitrogen has 3 bonds, so that's 6 electrons, lone pair of electrons, 8 electrons together. Okay, is it easier this way?
So those bonds are just in order to complete the octet?
Yes, in order to complete octet and draw the proper Lewis structure, yes.
So they're triple bonds or double bonds?
Triple bonds.
Because there's 3.
See them? Mm-hmm. There are 3, yes. So the double bond will look differently. Okay, so okay. Let's make the example of the double bond. Okay, so let's say we have this molecule here. Okay, so now we have a carbon number 1 and 2, 3, 4, 5, and 6. Okay, so we have 6 carbons here. We know that carbon 1 and 2 are connected to number 3, carbon number 3. Okay, so again, you draw carbon. This is going to be our carbon number 3, okay? Carbon 3. Maybe I will draw it differently this way. We have this is carbon number 3, okay? Well, 1, 2, 3, 4, 5, 6. I count 6. Do you see the number 2 here? That means the methyl group is counted twice. Okay, so if this is carbon number 3, that means the carbon number 1 and carbon number 2 are also connected to this carbon number 3. Okay, then carbon number 4 is connected to the carbon number 3 and carbon number 5. So this is 4. So now we have carbon number 5 here. Then the carbon number 5 is connected to carbon number 4 and the oxygen. So then we have an oxygen here. And the oxygen is connected to carbon number 6. Okay. Now we know that carbon 1 and 2 are methyl groups. So I'm just going to draw them. Okay. And 1 is connected to 3. So now carbon 1 has an octet. Same happens for carbon number 2. Okay. Now carbon number 3 is connected to number 4, so I'm going to just draw one line first. And carbon number 4 is connected to the hydrogen, so I'm going to draw it here. And also connected to carbon number 5. Carbon 5 now is connected to 2 hydrogens, so 1 and 2, and to the oxygen. So it has an octet now because it has 4 bonds. Oxygen is connected to the carbon number 6 that has 3 hydrogens. So going back from carbon 6 has an octet, oxygen has an octet, carbon 5 has an octet. Carbon 4 now doesn't have an octet because it has 7 electrons. So in order for it to have an octet, it has to pair the electrons from the carbon number 3. Okay, and in this case, it will make the carbon number 4 will give it an octet, and also carbon number 3 now will have an octet because it has 1, 2, 3, 4 bonds. Okay, so the line angle formula for this molecule will look like this. Okay, 1, 2, 3, 4, 5, 6. Any questions about that? Yeah.
Do we have to know why the line angle formula is bent like that, or not yet?
Not yet. Not yet.
Okay, thank you.
We will find out very quickly, so don't worry. Okay.
Thank you.
Okay, so let me minimize that now and share with you the next sets of slides. This guy here. And we are going to okay, so in here we have the another example of the different types of the line angle formulas that you need to draw for 5 different molecules here. Okay, so we have CH2, CH, CH, CH3, CH2, CH3. Okay, so if you think about it, we have a CH2. So that means that you have a carbon that is connected to 2 hydrogens, and then it has to be connected through the double bond to another CH. Okay, and then you have another CH, and CH3. Okay, and then CH2 and CH3. Okay, so the line angle formula for this molecule will look like this. Okay, so the second molecule that you have here is the C3H7OH, and it says both isomers. So the easiest way to do that is just, you just draw yourself a 3-carbon chain. So that's 3 carbons, and then you need an oxygen somewhere. So let's put it at the end. So OH at the end. Now you count number of the hydrogens, and it should be 3 plus 2 plus 2. That's 7 plus OH. So everything matches here. And you see in this molecule, you can have an OH either in the terminal carbon, or you can have it on the internal carbon. Okay. So the first one is called 1-propanol, the other one is called 2-propanol or isopropanol. Okay? And so what is the relationship between molecule A and B? Anybody? You cannot just say they are isomers. You have to say that they are constitutional isomers. And if you want to be specific, you can say that A is the primary alcohol, the B is the secondary alcohol. And again, this is something that you should know from the functional groups, okay? And they are both alcohols. But the idea here is that they have the same molecular formula, different structures. So that makes them constitutional isomers. Okay, the next molecule. Let me just copy that very quickly. The next molecule is CH3CH2CO CH2COOH. Okay, so I hope everybody knows that COOH, that's a carboxyl group now. So we have a CH3 CH2 CO CH2 COOH. Okay, so you see, once you get used to it, you can draw this molecule very quickly. Okay, so if we assume that this is carbon 1, so this is carbon 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, then you look at the next molecule here, CH3, CH2, CO, CH2, NH, CH3. Okay, so again, CH3, CH3 is here, okay, on the position 1, CH2 at the second position, then you have C, O, CH2 again, and then NH, and CH3. And the last one is called cyclohexane. So cyclohexane, that's a cyclic molecule made of 6 carbons, and it looks like that. If you want to be very specific, you can also draw something what is called the chair conformation, and we're going to talk about chair conformations. And I can just show you briefly how to draw it here, maybe too. So you just draw 2 parallel lines, another 2 parallel lines, and then you just connect them together. And these two are actually equivalent. Yeah? So the chair conformation is more like a real-life conformation that shows you the angles within the molecule. And we're going to talk about this, like why is it important later on when I talk about hybridization and then different stereoisomers. So let's move on now to the next part of the class, today's class, which is the valence shell electron pair repulsion theory. So this is the theory that allows you to predict the shape of the molecule. Okay. And this theory very often is used with something what is called the AXE method. So AXE method is the method that allows you to predict, again, the shape of the molecule around the central atom based on the substitution pattern around this atom. So A is your central atom, and X represents number of the ligands. So these are the elements that are connected to your central atom, and E is the number of lone pair of electrons. Okay, and based on that, you can predict the actual shape of the molecule. Okay, what is important in this theory that it assumes that atoms are surrounded by different regions of electron density, and those regions of electron density, they repel each other. So they want to be as far from one another as possible. The idea here is that the regions of electron density, these are actually your bonds or your lone pair of electrons. So each and every bond, when it forms, it combines two electrons. These two electrons, they have certain level of electron density, and that is associated. That depends on the type of the elements of the and that are connected with one another. So the cool thing about this AXE model is that if you just know the value for X and E, then you can very easily just use the table and predict the shape of the molecule. Okay. So if you have, here it says a steric number. So steric number, that's the number, that's your X number in your formula. So if you have a molecule, for example, that has the central atom, and it has only two ligands that are connected to it, and no lone pair of electrons, it's gonna have the linear structure, because those X's, those ligands, they want to be as far from one another as possible. Then if you have the steric number, so actually the steric number will be the number of your ligands and lone pair of electrons together. Okay, if it's equal 3, and you have 3 different ligands connected to your central atom, then you have a trigonal planar structure, or it can also be band structure. And it's band because in the second example here, we have 1 lone pair of electrons. So in this theory, the lone pair of electrons does not affect the structure of the molecule. Okay, it just basically to predict the structure here, you just have to assume that it's an empty space, which is of course not true, but for this theory purposes, this is what happens here. Okay, because now 2 of the ligands are as you can see here, band. Okay, and then if you have 4 different substituents, you can have either tetrahedral or trigonal pyramidal if you have 1 lone pair of electrons, or another band if you have 2 lone pair of electrons. And in this class, we are going to be interested only in the first 3 scenarios. Okay, you see, like, there are some other options for like 5, 6, and 7 substituents around the central atom. You just need to be aware that they could be there, but we are not going to use them in the predictions that in our exams. And the reasons for that is simply because we are dealing mostly with the carbon-based molecules here, and they tend to have the tetrahedral structures or trigonal planar or linear. Okay, sometimes band too, if you have an alcohol, for example. Okay, and in the next slide, you have an example of different types of the molecules and their shape. So, for example, if you have the molecule that has an AX2E0 AXE model values, or then we know that this is basically AX2 scenario, so it's a linear molecule, and some of the examples of those are presented here. Okay, so for example, carbon dioxide, it's a linear molecule, and if you draw the structure of carbon dioxide, you will see that this is carbon, double bond one way, double bond the other way. When we talk about hybridizations, I'm going to show you why is it this way, not the other way. Why is it not bent, for example? Okay, and then you have the steric number here is 3, so you have two ligands and one lone pair of electrons. And so some of the examples of that could be, for example, ozone, or it says carbon dichloride, for example. Also it could be like, what else could it be? Yeah, so these are actually quite a good examples. Okay, so then you have the steric number 4 with 2 lone pair of electrons and 2 ligands, and here we have, for example, water as the example. So imagine you have a water which is oxygen connected to 2 hydrogens, and you have 2 lone pair of electrons. Okay, that's what makes the water bend, and so on, so on. So basically, from this particular table, again, we are interested in that part of the table. You will be able to see that. I don't know if this is gonna help too much. Yeah, does it help? Yeah. So the idea here is that we are going to be interested in only the molecule that have a steric number up to 4. Okay. So anything that has more than 4, you need to be aware of it, but not necessarily. It's not going to be needed for your exam. And the reason for that is simply because we want to have the I want you to be able to recognize tetrahedral structures, trigonal pyramidal, trigonal planar, linear structures, bend structures, this kind of stuff. Okay. And again, we're gonna talk about that, later when I talk about hybridization. So going back here, okay. So imagine the situation now that we have, for example, a molecule called PCl5. Okay. So actually, no, I cannot do that here for you. Okay, so let's do something different here. Because I told you that I won't be doing that. So PCl3, for example, okay? If you were to draw the Lewis structure of PCl3, what would it look like? Anybody? What is the group number for phosphorus?
So P would have two lone pair electrons and 3 single bonds.
So P has 5 valence electrons, correct? So you have 1, 2, 3, 4, and 5. Okay. Chlorine has 7, but it forms only single bonds with the phosphorus. Okay. So I'm just going to draw chlorines here. You just need to remember that each and every chlorine is surrounded by 7 electrons. In this case, 6 plus a single bond, which adds to 8 electrons. But the fact that you form only a single bond here is because you share 1 electron with the phosphorus here. Okay. So what will be the AXE value here for the PCl3? So X will be 3, and E, well, how many lone pair of electrons do you have here? 1. So, okay. So now we know that this is basically what it is. Okay. So the question is now, what is the shape of this molecule? it's going to be trigonal pyramidal, okay? Correct. So this is basically how you solve those problems. You will have the you will have the access to your tables, you know, with the you know, that I just posted for you. If you are interested in more different shapes, you can also get it from the Wikipedia, I believe, yeah. And the only thing you need to be aware of that when you draw your molecule, okay, you need to draw the proper Lewis structures with right number of the lone pair of electrons. So you can assign the AXE value and then just read it from the table, you know, read the actual shape of it, okay? So this is what I want you to be capable of doing. So this is basically when, you know, when you will be dealing on your exam with the VSEPR theory, it's more or less, it will depend on your ability to draw the proper Lewis structure. So if you can draw the proper Lewis structure, then you should have no problems to assign assign the AXE model. The E is the number of the lone pair of electrons. So 2 electrons, 1 lone pair. Okay. So E represents the number of the lone pair of electrons, and we have only 1 lone pair of electron here, so therefore the value of E is 1. And the X is the number of substituents, correct. So there's one thing that you have to be aware of. So for example, do you remember, like, we were talking about this guy here, yeah? So dimethyl sulfate, yeah? I'm sorry, dimethyl sulfoxide, yeah, so DMSO. DMSO here has a double bond, for example, between oxygen and sulfur. In VSEPR theory, you do not count the double bonds as 2 bonds. So the X is equal to 1 for the double bond, and also for the triple bond. So the X value here will be 3. If you have acetonitrile, okay, and you're interested in the X value for this carbon here, the X will equal to 2, because the triple bond here counts as 1 bond. Okay, this is important for you. Okay, so you want to make sure that you don't forget that. You don't count here like 3 bonds, so and plus 1, that's 4, so X4. No, that's why this molecule here has a 180 degree here, and it's a linear molecule. Okay. So for example, the A value will be 1, and A value is always 1 for in AXE model. So what is the E value here for the acetonitrile, for the carbon? Zero, no length pair of electrons. Wonderful. Okay, so so this is something that you just have to keep practicing. Okay, so honestly, the best way to do that would be, when you practice your Lewis structures, just assign by default the AXE number. This way you will know for sure that you got it, and this question on the exam will take you only like a few minutes. Okay. So now let's go back to the shapes of the orbitals. Okay. So do you remember when I told you that we have S orbitals, P orbitals, D orbitals, and F orbitals? And we are interested mostly in S and P orbitals because these are the orbitals that are involved the most in organic synthesis, basically. Okay. So the bond formations in organic molecules. So the S orbitals are spherical. And here we have an example of a 1s and a 2s orbital. So you see both. This is 1s. It's smaller than 2s. And both of them are, spheres. The purple area here indicates the volume where the density of where the probability of finding the electrons is the highest. Okay, The blue area here, it's a node, so that means that there's in this blue area there is no way you can find the electrons. Okay, so therefore it's like the 2s orbital, for example, is it's kind of like an empty sphere. Okay, so only in the purple area the electrons can exist. In the blue one, it may not. And because of that, the 2s orbitals is higher in energy than 3s. 3s is higher than 2s, and so on and so on. And therefore, there you have the larger radius. Okay, so 1s orbital will be the smallest, and then 2s will be bigger, 3s will be even bigger, and so on and so on. Okay. And this is, of course, the electron density map that has been calculated. So that means that somebody used the computational analysis, most likely using some sort of a Schrödinger equation, to calculate the probability of finding those electrons within this volume. Okay, and by doing so, they confirm that the shape of the s orbitals is spherical, and also, like they confirm the shapes of the other orbitals that that were calculated, and here we have the shapes of different p orbitals. So the p orbitals look like these little 8s here. Okay, each and every one of these p orbitals is located along the axis. So we have an x-axis, a y-axis, and z-axis. And the different colors on those orbitals, that means that they have a different wave function number. Okay, so some of them are positive, some negative. Actually, it doesn't matter which one is which in this, as long as you remember, when you assign it, as long as you remember which one you assign to which part. Okay. So by default, we can, let's say that red one is positive, blue one is negative, or blue one is negative, red one is positive. Doesn't matter really here, as long as you are consistent in your all observations. And if you combine all those three p orbitals, you have this this three-dimensional structure with the p orbitals facing, in every directions along the axis number. So this is very important information to you, because because each and every one of these p orbitals can then interact with another, let's say, s orbital, for example, to form bonds. And some of them can form pi bonds, which are the side-to-side interactions, and some of them can form a sigma bonds, where are head interactions of the orbitals. And we're going to talk about it in a moment. Okay. So now we're going to move to the hybridization theory. Okay, so the hybridization theory relies on the valence bond theory, that basically tells you that the bonds are formed only between valence electrons within the molecule, within the atoms. I'm sorry, yeah. So the atoms can share only valence electrons. Okay, and in this theory also the electrons are localized between two atoms that forms the bond. Okay, so the bonds are also localized between both of the atoms that forms the particular bond. It doesn't matter if it's a sigma or pi bond in this case. Okay, and basically that you have, when you use the valence orbital theory, you just basically assume that drawing the line between two different two different atoms indicates that there are two bonds, two electrons that are shared now together. But there is one problem with this theory. Okay, so this theory assumes that only p and s orbitals they kind of like they interact with each other. So for example, if you have a carbon, okay, so if you use only p orbitals as the valence orbitals for the carbon, and you react them with, let's say, s orbitals from hydrogens, you would expect only 3 bonds to form, not 4. And we know that the carbon forms 4 bonds, where in its neutral state. Yes. So, for example, there's a methane, but not CH3 as a free molecule without the charge. And also another thing is that you would expect that those bonds will have a different angles, and it turns out that those angles that would be expected will be about 90 degrees, and we very rarely observe 90 degrees angles in the molecule. So one of the examples of those 90 degrees would be, for example, a planar complexes of platinum. But in carbon-based molecules, you do not see 90 degrees. Okay, you can see 120 degrees, you can see 180 degrees, you can see 109, but never 90. Okay, and there is the reason for that. I mean, almost never 90. Okay, so there is the reason for that, and the reason has been explained as the formation of so-called the hybrid orbitals. So what are the hybrid orbitals? So hybrid orbitals are the mathematical combination of 2s and 2p orbitals. So if you take, for example, one 2s orbital and 3 2p orbitals, and you hybridize them together, you form a total of 4 different new hybridized orbitals. Okay, and then they will have the same energy, the same let's say availability for the atoms to react with them, and the same probability, for example, to share those electrons with with another elements within the molecule. And in methane, for example, they will basically interact with 4 different hydrogens, and those 4 different hydrogens, they will try to repel each other, and therefore the structure that will form will be tetrahedral. Okay, and so let's talk a little bit about how the hybridization actually work. Okay, so we have in general 3 different types of sp hybridization type. Okay, so we have sp3, sp2, and sp hybridization. At first, I'm going to talk about sp3 hybridizations, where 1s orbital and 3p orbitals are mixed together. When they are mixed together, there are 4 sp3 hybrid orbitals formed. So s plus 3p, that's 4. Yeah, so 1 plus 3, that's 4. Yeah, and those hybrid orbitals, they have lower energy than p orbitals, but higher energy than s orbitals. But they are all equal in energy. So if this is for example, electron configuration of carbon. So we know that the electron configuration of carbon is 1s2, 2s2, 2p2. And we know that 2s and 2p electrons are the valence electrons. And this is what you see as the pink arrows here. So you would expect that in the normal situation where there is no hybridization, well, that that 2s orbital will hold 2 electrons, and the 2p orbitals will hold another 2 ampere electrons. And in reality, you have 4 different hybridized orbitals that have the same energy, that all of the electrons are unpaired over there. And each and every one of them can react with another electrons, for example, for hydrogen or another carbon, and can be paired to form the bond. So each and every one of these paired structures here represents a different bond that formed, and it's only a sigma bond. So the sigma bond is a single bond. Okay, so that's another way to say a single bond. And the sigma bonds are the head-to-head interactions of the p orbitals. So, for example, if you have let's call it the sp x orbital, okay, from sp3 hybridized orbitals, it's going to react with another spx orbital along the x-axis. But this spx will not react with, for example, orbital that goes toward the y-axis. So that will be spy orbital. And the reason for that is because the geometry doesn't match. So that's why, you know, the head-to-head interactions along the same axis with the right sign of the wave function that has to be the same, basically, will give you a sigma bond. And the structure of the sp3 hybridized molecules or atoms is tetrahedral. So you see the p orbital is a symmetrical kind of like H-shaped molecule. sp3 orbital looks very similar, but you see that the proportions are changed a little bit. Okay, so one part is slightly larger than the other. And because of that, you know, like now we have 4 different orbitals that have the same energy, and you can show it as a cartoon here as with these little balloons, and you can clearly see here that it forms the tetrahedral shape, where in the middle you have a central atom. This is your carbon, for example, okay? And in each direction, up and then along those axes that are shown here as the black arrows, one of the bonds can be formed. So in the, for example, in the methane, where you have a CH4, you have a carbon. One hydrogen goes up, the other one goes another direction, and then you have one that goes away and one that goes toward you. The dashes means that something is behind the plane of the board here, or like whiteboard here, and then the wedge here indicates that something is above the plane. Okay. And so like I said, the shape is tetrahedral with sp3 hybridized atoms. Okay, and so this is something that you really have to remember. Okay, so how do you know that the particular, let's say, carbon in your molecule is sp3 hybridized? It's very simple. You just look at the number of the single bonds that are connected to the carbon. If there are 4 single bonds, that means that this is tetrahedral, so it's sp3 hybridized. There are some exceptions for that, and I'm going to show you those too. Okay, and here exactly, you know, this is exactly what we were talking about. But you know, based on the 3 different molecules, so we have a methane molecule, carbon, hydrogens are going away, each and as far from one another, and form the tetrahedral structure. But then you have an ammonia, for example. So do you remember, according to the VSEPR theory, the ammonia is a trigonal pyramidal structure. According to hybridization theory, or the valence bond theory, it's tetrahedral. Because you have now this lone pair of electrons that basically occupies the space and it's being accounted for. And the same comes for the water molecule. So the water molecule, according to VSEPR, is the band structure, but according to hybridization, it's gonna be tetrahedral. Okay? And you see, like, the difference between all these 3 molecules is basically the what occupies the empty in this case the sp3 orbitals. So just 1 lone pair of electrons in ammonia and 2 lone pair of electrons in water. And what is the angle? Well, in the ideal situations, like in methane, for example, where all the substituents are the same, the angle is 109.5 degrees. between each and every element in the structure. Okay. The presence of the lone pair of electrons, because they have higher electron density, they repulse the other substituents a little bit more. Therefore, it changes the angle. And you see, if you have one lone pair of electrons, the angle changes to 107. If you have two lone pair of electrons, it changes to 105. So do you need to remember that? Okay, so I would say in general, you need to know that the lone pair of electrons will affect the angle of the between the substituents in sp3 hybridized molecules, but you don't have to remember the actual values, like for ammonia or water. You do need to remember the 109.5 value for the tetrahedral carbon. Okay, so this is the ideal situation. Okay, so what happens if you have, for example, a mix of only two p orbitals with one s orbital? Well, then you form something what's called an sp2 hybridized hybrid orbitals, and one of the p orbitals remain intact. Okay, so what does it mean to you? Okay, so if you think about this, is again electron configuration for carbon. That means that you have free bonds that will form as a sigma bond, and then you have one orbital available for something what's called the pi bond formation. So the sigma bond formation is the head-to-head interaction. Pi bond formation is the side-to-side interactions of the orbitals. Okay. And here is the example of the shape of sp2 hybridized molecule. So again, the shape of the sp2 hybridized orbital is slightly different than just the p orbital, and the structure of it is a trigonal planar. So that means that all of those sp2 hybridized, free sp2 hybridized orbitals that are present by the hybridizing two p orbitals and one s orbital, they combine together and then they form this nice flat structure. Perpendicular to this structure, there is this remaining p orbital that hasn't been hybridized, and you see it in the right here. Okay. So to tell you the truth, like as far as the hybridization is just the way to explain the behavior of different molecules. Okay, it's not about the reason why the molecules actually tend to hybridize is just because they want to form those bonds that have they want to bind to other molecules with the lowest possible energy. And sometimes this can be achieved only by formation of the, let's say, single bonds. But in other molecules, you have to create other types of bonding. So double bonds, for example, or triple bonds. And the hybridization explains how those double and triple bonds are formed. Okay, does it help you a little bit? Number of the lone pairs plus the number of sigma bonds atom. Okay, so in the hybridization is calculated based on the number of the shared s and p orbitals. Okay, so if you hybridize two p orbitals and one s, that's going to be sp2. If you hybridize one s orbital and one p, that's going to be sp hybridization. But in practice, it's relatively simple. Okay, so if you have a molecule, for example, if you have a molecule, for example, that has the 4 different bonds, This carbon, this carbon here is sp free hybridized. Okay. If you have a molecule that has a double bond, this carbon here will be sp2 hybridized. But also, this carbon here will be sp2. Okay, because now you have a pi bond. I'm going to talk about the pi bond just in a second. Okay, and then you have a triple bond. So this guy here and this guy here are sp hybridized, and the reason for that is simply because now you have two pi bonds. So so double bond sp2, triple bond sp, basically. Like to make it simple. But the reason for that is simply because of the fact that that there is a different number of s and p orbitals that are being hybridized together. Okay. So here is the example of the sp2 hybridized molecule that is the BH3. Yeah. And you see that BH3 here is a trigonal planar because it binds only to 3 hydrogens, and then it has an empty p orbital. Okay, so it's not involved in the hybridization. Therefore, this is actually a good example of the correlation between VSEPR and the hybridization, but it's not always the case. Okay. In this case, we can clearly see here that we have just 3 sigma bonds. Okay, so 3 sigma bonds. That means that you have the 3 hybridized orbitals. To have the 3 hybridized orbitals, you have to have sp2, because s is 1 orbital and p2 that's 2, so together it's 3. Yeah, and that means that there is 1 remaining p orbital that is unoccupied by electrons. Here is the example of the ethylene. Okay, so we have a carbon, double bond, carbon bond. The angles between those, between the hydrogen and the carbon here are roughly about 120 degrees. Okay, and both of the carbons in these molecules are sp2 hybridized. There are 2 different types of bonding here formed. One of those bonds is the sigma bond, and the other one is called the pi bond. So the sigma bond is this bond here in between, and also the bonds that are formed between the carbons and also between the carbon and hydrogens. These are sigma bonds where you have a head-to-head interaction of the in this case sp2 hybridized orbitals with either another sp2 or with the s orbitals from the hydrogen. And you see on the right, in the red and blue, you have the p orbitals that are overlapping sideways with one another. This is your pi bond. As you can imagine, the interaction head-to-head in the sigma bonds is a stronger interaction than the side-to-side interaction of the pi bonds. And that's what makes the double bonds more reactive compared to the single bonds. But do not get confused with the reactivity and the strength of the bond, because the double bond strength is higher than a sigma bond, because on top of the sigma bonds you add the strength of the pi bond. But in order to break the pi bond, so the pi bonds has the lower strength than the sigma bond. So I know it might be confusing a little bit, but like sometimes when you look at your textbook, textbook sometimes they say, oh, the double bond is stronger. So if it's stronger, why is it more reactive than the single bond? And it's not that the double bond itself is weaker. It's just the pi bond in the double bond is weaker than the sigma bond. Okay. And here is just a graphical representation of the double bond. Hybridization. Well, in organic molecules, we always assume that there is a hybridization going on there. Okay, it's either going to be sp3, sp2, or sp. So this is the last example. This is the sp hybridization, where you have when you have one s orbital and one p orbital, and you see you form two sp orbitals, one s and p, so two sp orbitals, and then two p orbitals unoccupied, unchanged. I'm sorry. Yes. So that means that you have now the molecule that can form only two sigma bonds and two pi bonds. So just by that, you should know that, oh, sp that must be a triple bond or something else. Okay. And then I'm going to show you what is this something else. So in the sp hybridized molecule, you have those two sp orbitals that are in line here. Okay, so they go along the axis. Usually it shows it's being shown as an x-axis. It doesn't matter as long as it's along the same axis. Okay, and then you have this py orbital and pz orbitals that are perpendicular to one another and also perpendicular to the s and p sp orbitals. Okay, so we know that now each and every one of these p orbitals can have a side-to-side interaction with another p orbitals, and an sp orbitals can form the sigma bonds with another another parts of the molecules. So here is the structure of the actually there is a triple bond here. Yes, so this is carbon, triple bond, carbon, hydrogen, hydrogen. I'm sorry, I forgot to rewrite that. Yes, so maybe I can do that here. No, okay. So basically, this bond here in this molecule here, the CH bond, and the one, let's call it in the middle, these are your sp hybridized orbitals that are involved in the formation of the sigma bonds. So the green ones are sigma bonds, and let's make it blue, okay? And then you have two pi bonds, this guy here and this guy here. So the blue are pi bonds, and there are two of them, okay? So we have two sigma bonds now connected to this particular carbon, and actually both of them, and two pi bonds that are connected between these two carbons. Okay, that's what makes it actually easier for you to recognize the hybridization, because you look at this molecule here and you say, oh, okay, I have a triple bond. That means that at least one element over there has to be sp. Actually, two elements has to be sp hybridized. Okay. There are some exceptions for from the rule, and the molecules that are called alleles. Yeah, so if you have, for example, a CH2 CH2 molecule, okay, this particular molecule can exist as the molecule that has now two double bonds to the central carbon in the middle. Okay, so how is it possible that you can form two double bonds here? Well, that is possible because, for example, I'm gonna label it with red here. So, for example, if we assume that these are in red are sigma bonds, these sigma bonds are using sp, let's say the SPX direction, okay? And so that means that there is the pi bond here that there are actually two pi bonds that has not been hybridized, and one of those pi bonds can interact with another pi bond from, let's say, a terminal carbon on the right side, and the other one can interact with another that is now perpendicular to that. Okay. You cannot draw the carbons I'm going to draw it schematically now. Okay, you cannot draw the carbons with the same directions of the pi bonds, bind them together and claim that both of them are double bonds. That can be used only if you draw the resonance, and we're going to talk about it. Okay, so this would be a wrong way of drawing the molecule. You have to show that, you know, like that let's say this is going to be, let's say, a y, and this is going to z direction. So the y interacts with y, and z interacts with the z orbital. Does it make sense to you? Okay, so I think this is going to be the last slide for today, and we're gonna talk about more of this material tomorrow, and also I'm also gonna talk about the other and we're also gonna talk about other stuff that that will, honestly I don't remember what it is yet, so we'll see. Okay.